Our first topic for the third unit in this course is all about the mole. Now we looked at a couple of videos from YouTube on what the mole is, so you should have a little bit of an understanding of what it is and how to start to use it. So we're going to start to use it today, and for sure lots in the next video. So what exactly is a mole? Well, if we look at the concept of a dozen, we know that's pretty easy. You can have a dozen muffins or a dozen cookies, a dozen eggs, a dozen roses, and everybody knows as soon as you say the word dozen, you know that means 12. Well, if you're a chemist, you will start to learn really, really quickly in this course that a mole is actually 6.022 times 10 to the 23. So you can fill that in your notes. Its actual definition is the number of carbon-12 atoms that is needed to have a mass of 12 grams. That's where it comes from. But for now, here's what you need to know. You need to know about this Avogadro's constant, okay, which is also dubbed capital N with a subscript capital A. That's the same thing as that number there, which is the same thing as a mole. The way we abbreviate mole is MOL. So you'll see that. So when I ask you to make sure you put your units in, the units or the symbol for mole is just MOL. So examples, like I said before, if you have a dozen eggs, you know you have exactly 12 eggs in your carton. So what you're learning now is that if you have a mole of atoms, you actually have 6.022 times 10 to the 23 atoms. So let's start to think about that in terms of calculations. Here's a quick example here. How many atoms are there in 2 moles of potassium? So if we write down what we know that if we have 1 mole of potassium, that is the same as 6.022 times 10 to the 23 atoms. Okay, so now my question is, what happens if you have 2 moles of potassium? How many atoms would that equal? So it actually ends up being 6.022 times 10 to the 23 times 2. So we're going to take that whole thing times 2. When you do that, you get 1.2, I think 044 times 10 to the 24. Atoms. Okay, so in this unit, a couple of things you guys need to be doing when you're watching these videos. Number 1, you need to have a calculator in front of you, and you need to actually punch in these numbers here into your calculator and make sure you're getting the same answer as me. If you don't do that, I guarantee you are not going to be successful in this course. So don't be lazy. Take 2 seconds out of the time that you're watching this video, punch these numbers into your calculator as we go through, and do that for the remainder of the course. It will help you out immensely. Second thing, you have to always remember to put in your units at the end, and you need to have the right number of significant figures. So if I gave you, or if you gave me this answer, this would actually not have the right number of significant figures, because if you look up in my question, I have 4 significant figures in my question there, so I need to have 4 in my final answer, which means I have to round this to 1.204. times 10 to the 24 atoms. So that should be my final answer, and that would be what I'm giving you your marks on. If you're missing that, then you are going to lose some marks in this course. All right, oops. Come on. There we go. So basically, how do we convert moles to number of particles like I just showed you? There's a couple of different ways you can do it. You can kind of figure it out like I just did in the last example with potassium, figured out I needed to multiply it by 2. Or we can use this formula here. So you have to remember, if I know the number of dozens, so if I have 3 dozen eggs, for example, I can figure out how many individual items I have by taking 3 times however much is in a dozen. Same thing will apply to moles. So if I know I have 3 moles of something, and I know what a mole is, 6.022 times 10 to the 23, I know that I can take those 2 numbers, multiply them together, and get the number of individual particles. The other thing you can do, you can use conversion factors, which we're going to learn a little bit more about in the next video. Or for now, you can use this formula, okay? So small n is the amount in moles, okay? And that's always equal to n, which is the number of particles, divided by Na, which is Avogadro's constant, which is 6.022 times 10 to the 23. So if you can rearrange this formula around, you can actually solve for a lot of these problems, okay? Now I'm going to be teaching a lot of conversion factor method in class. We've already done quite a bit of unit conversions already. But here, let's take a look at this example here. Work for me, there we go. So this is the last example in your notes. A Canadian penny, I can tell you right now, contains 0.106 moles of copper. So how many atoms are copper in a Canadian penny? So for now, what we can do is look at using that formula. So the formula I just gave you on the last slide, you should have that written in your notes. N equals capital N over NA. Okay, so if I want to find, in this case, the number of individual atoms of copper, I'm actually looking to find this here. So I can rearrange my formula and get that capital N is small n, which is number of moles, times Na, which is Avogadro's constant. Okay, so if I do that, I should be able to get the number of atoms. So I'm actually going to take that number. So N, my number of moles, is 0.106. And notice I'm putting in my units, okay? And Avogadro's number is 6.02 times 10 to the 23. And this can be, in this case, atoms. Okay? So if I take that on my calculator, you get 6.3812 times 10 to the 22 atoms. So that's sort of what came straight out on my calculator, but that's not my final answer because I have to round to 3 significant figures, okay? So in this case, my final answer, I'll do it in a different color just to show you. I have to round it to, there's 3 there, there's 3 there, so 6.38 times 10 to the 22 atoms would be my final answer, okay? That one there is my good one. Check, I'm done. So there's a formula for you to use. If you like using formulas, I will mention them briefly, but I'm also going to show you how to do a conversion factor method. So we'll do more of that in the next video. So, oops. There we go. So in this video, you should have learned a little bit about Avogadro's constant, which is the same as 1 mole, which is the same as 6.02 times 10 to the 23. Notice I dropped one of the 2's there. That's just because the most common way we write Avogadro's number is only with 2 decimal places after the 6. So it's up to you if you want to put 6.02 or 6.022. That's fine. So those are all equal to each other. You need to know the difference between a molecule and a formula unit. I'll explain that really quickly right now because I know this isn't really in your notes. A molecule is basically the word we use, I'm going to erase that, to apply to a covalent compound or a molecular compound. So something that's made up of only non-metals. So an example is carbon dioxide. Okay. A formula unit is a term we use to describe the number of units for ionic compounds. And remember from Unit 1 that an ionic compound is a metal and a nonmetal, so an example would be something like calcium chloride. Okay. So if I'm talking about calcium chloride or an ionic compound, I'll use the term formula unit. If I'm talking about a covalent compound, I'll use the term molecule. And if I'm talking about an element straight off the periodic table, I will use the term the number of atoms. So you're going to see that a lot more in class and as we go through our worksheets. That's it for this video.